Okay, so we have talked a lot about the clocking, the analog to digital conversion, PWM and so on capabilities of microcontrollers. A very important aspect of all of this is the timer subsystems that are present, right? So what are timers? They are basically very versatile peripherals that are invariably present in most microcontrollers. They can be used for many things, including things like generating arbitrary delays, for pulse width modulation, of course, right, as we have seen as an example. They can be used for certain things like event counting, basically for measuring frequencies and so on, okay, and for certain forms of input capture. Output events, right, pulse width modulation is a specific type of event in the sense that it's just a duty cycle, but instead I could also have something which basically counts for a certain amount of time and then just triggers one pulse to say, hey, I'm done with the work now, or certain amount of time has passed, do some work, okay, maybe sample a signal and store that value somewhere, right. And they can also be used for timekeeping, just keeping track of how much time has passed, and in particular there is one very specific sort of application of this called a watchdog timer that we will look at later. So timers, like I said, are very common in microcontrollers. The STM32 microcontrollers in particular have different types of timers, right? And if you look through the actual reference manual for the the data sheet of the STM32, you will find that there are, for example, something called TIM1, which is the timer 1 or the advanced control timer, right? There are a few terms over here that I want to sort of just pick on and elaborate, but for the most part the only way to really fully understand what timers are capable of is to go through the data sheets in a fair amount of detail. It differs quite a bit from one microcontroller to the next, so what I am doing is trying to cover the sort of core concepts. And what you will need to do when you actually need to use a microcontroller will be to be able to pick up the data sheet and find out what are the relevant terms and features that you need to know, right? There are many advanced operation modes. Some of them I'll be briefly talking about, but for the most part they also differ from one microcontroller to another. The important point about a timer is that it operates independent of the CPU. What does that mean? It means that the CPU is not actually executing instructions to count. There is no sort of instruction. In fact, the CPU could be completely asleep. It could be turned off and the timer circuitry would still be active, right? It is separate hardware and completely independent, and the different timers are also independent of each other. Why is that useful? Because what it says is it helps me with things like power management. I can actually have the CPU basically go into a deep sleep mode while some timer is actually still active and counting, right? And once the timer hits some kind of threshold, it can generate a signal to wake up the CPU, do something, and then go back again to sleep, okay? So for example, as we can see, the advanced control timer, what does it do? It's a 16-bit counter. So what can we infer from that? The fact that it's a 16-bit counter basically means that it can count from 0 up to 65,535 and then back again, right? That basically tells me a couple of interesting things. One is that if I was to give it a 48 megahertz clock input to that timer, it would elapse pretty fast, because 65,000 of that is probably a little over a millisecond or so, right? And that's it. That's the maximum that I can basically have. But that's where prescalers come into the picture. I can take that 48 megahertz, prescale it down to a lower frequency, and then tell the timer, hey, use this prescaler and then use this as the period of the timer, right? What does the period of the timer do? It basically says that it will count up to a certain value and then reset, okay? And this resetting can also be done in a certain way where you could also have it as a down counter. It basically starts off with one value, counts down to 0, and then again goes back and counts again, meaning that it can even automatically reload the value that you want it to start from, right? So you could either have a compare value where it basically stops and then comes back, or you could have an automatic starting point and then count down and then flip up again. At the same time, it also has different kinds of comparison registers, right? So there is output compare, where you can basically check the value that you have reached in your counting, and if it has crossed a certain value, right, somewhere here, I turn on or off a particular signal, which is how I generate PWM, right? So things like it can be used for input capture, where I could, for example, just have the counter going up, and it can be used to measure the pulse length of input signal. So whenever the let's say that I have a counter that's going up to a certain value, and at some point in time this input signal comes in, right? I can just basically use that as an event to find out, okay, what was the value in the counter, and this number out here tells me the either the timestamp or the length of the signal, right? How do I get the length of the signal? So for example, I could start trigger over here when the signal starts, and then find out at which point it, let's say, the signal stops, right? I could basically count that many cycles, and it would give me an estimate of how long the signal was high. Okay, the TIM3 in this case, in the case of there's no TIM2, it turns out they have some specific numbering that they use for the different timers, but you have to look at the data sheet to find out which timers are actually present in any given microcontroller. It looks very similar to TIM1 on the face of it. It also says 16-bit auto preload programmable prescaler, right? But it has slightly fewer functionalities. If you look at it, the advanced functionality over here is actually given in TIM1, whereas over here TIM3 is what they call a general purpose timer, right? It does not have some of the advanced functionalities that are present in this, although you will see that things like the PWM, input capture and so on are basically common to both the timers, right? So how do you use a timer? There are many things that you need to do. Again, there will be registers, configuration registers, that you need to set certain values for, right? Which basically comes down to things like what is the clock source, in particular what kind of prescaler to use, right? How much should you bring the clock source down so that it fits into a sort of valid range that you can use. You can change the mode of the counter to things like up counting, down counting, or you could automatically tell it that once it compares with a certain value, flip from on to off, and therefore create a signal of a certain duty cycle, therefore PWM, right? All of these is just like one register setting somewhere that allows you to control how the timer behaves. You can, as I said, specify the prescaler to bring down the clock counting period, as well as the period over which the, let's say, PWM or counting needs to happen, right? Timers can also be used for one very specific and useful purpose, which is to generate what is called a timer interrupt, right? Interrupts are things that we have not spoken about so far. We will be talking about it later because they are a very important usage mode of microcontrollers, right? And they are a very powerful construct, but on the other hand, it requires a little bit more discussion. So for the time being, I'm not getting into that. Now, there is one particular use case of a timer which I just want to sort of talk about briefly, which is that occasionally, either due to bad code or due to errors in your hardware, you can end up with what's called a hanging system, right? The notion of a computer hanging is something that most of us, anybody who's interacted with any kind of computing system for a non-trivial amount of time, will be familiar with, right? Either your phone stops working, or something doesn't work the way that it's expected to, and we say, hey, it's hanging. What do we do when it's hanging? We restart the system. Okay, now we have got so used to the idea of something hangs and we restarts it that we don't think too much about it, except when you are trying to build a system that you don't have access to, right? And one of the most sort of interesting examples of that was in the news a few months ago was the Voyager spacecraft, right? Voyager spacecraft were launched in the late 70s. They are now the farthest spacecraft from Earth that exist currently, right? And they are still flying away from Earth at a tremendous speed, which basically means there is absolutely no chance of going there and restarting the system, not even of communicating with it. It takes basically hours for a signal that is sent from here to even reach the spacecraft, right? So in such a scenario, what do you do? I mean, once you have launched a spacecraft and nobody can go and physically turn it on and off, but it hangs because there was a bug in the code, or there was a hardware error that you could not have foreseen, right? Something happened. There are things called single event upsets, alpha ray particles hitting the system and so on. which can cause it to behave strangely, right? And what happens? Maybe the code that was supposed to be while something less than 0, or while something greater than 0 may be changed into while something less than 0, and the condition never gets satisfied, and the code just sits over there waiting, never gets out of the while loop. Okay, that can happen. I mean, it has happened multiple times to the point where you definitely don't dismiss it as something which is impossible. Okay. Now, what do you do in such a scenario? Yes, you want to restart the system, but nobody can physically reach the system. So one possible solution is that you bring what's called a timeout, right? And you say that, look, if a certain amount of time has passed and the system is not responding, just force reset it. But then comes the question, who's going to handle the timeout, right? It can't be the CPU, because the CPU is the one that's actually hanging out there. This is where the independent timers that are available in microcontrollers come into play, right? And in particular, many microcontrollers have this thing called a watchdog timer. It runs independent of the CPU and usually counts down from some number until it hits 0. If it ever hits 0, the idea is there was a problem, right? And the way that we think about it, or the terminology that is used, is the main program must sort of pat the watchdog at regular intervals. Okay, this is just, to make it sound nice, but pat the watch, because we call it a watchdog because its only purpose is to sort of watch the behavior of the circuit and bring it back if it is sort of not behaving the way it's supposed to. So what does patting the watchdog mean? It means you need to basically do something to that timer to reset it back to its original value so that it starts counting down again. That would be as simple as maybe writing a value into one particular register. All that we are saying is the main program must have something where on a regular basis it's going to do that, right? Which is actually fairly reasonable, right? Because the main program will be doing some other functionality. All that you need to do is, after every maybe function calls, or after some number of things, or maybe there is some other timer interrupt that comes along and schedules different tasks onto it, it needs to once in a while make sure that it goes and tells the watchdog timer, hey, everything is all right. Okay, if it does not, the watchdog timer hits 0, it assumes that something went wrong and just force resets the entire system. Okay, which is, all that you need to do is make sure that your timeout has been set long enough to avoid just unnecessarily resetting your system, right? So you put it to a long interval, maybe several seconds or minutes, some time interval that's long enough that you can be sure that if your CPU hasn't responded within that time, something is wrong. Okay. So what are the use cases? Especially in embedded systems, especially in the context of safety critical and more importantly unattended operation systems, right? Things where it may not be physically possible for someone to go examine it and reset it if necessary. You need to use watchdog timers, right? If it's just something like your microwave oven or your television remote control, you probably don't care about watchdog timers because someone's always physically using the thing, right? And if it's not working, they can take care of switching it off and on. But if it's something that has been deployed in, let's say, deep in a mine or in a nuclear plant or something of that sort, it's not always possible for a person to get there within a few seconds or even minutes to restart the system, right? So the benefits of having watchdog timers, obviously reliability, error state detection, and most importantly automatic recovery, right? You can actually restart the system rather than just sort of saying, hey, something went wrong and giving up over there. But obviously it comes with its own drawbacks, right? The biggest problem that you need to be aware of and careful about is, are you going to end up getting false resets, right? Just because you put your timeout too low, right? It didn't give it enough time to actually finish the work and just ended up resetting even though the CPU was actually busy doing some computation. Then that becomes a problem. It also gives you limited debugging visibility because it just restarts the system. It doesn't necessarily tell you what went wrong, right? And in fact, unfortunately, the CPU itself was hanging, it was stuck. So it's quite possible there was no way to get that information of what went wrong, but it does limit your debugging capabilities. And in certain kinds of applications, especially ultra low power systems, just having a watchdog itself can be a problem, because that's another source of a power draw, right? But obviously it's a trade-off, right? Like everything else in engineering design, you need to decide whether the benefits of having the watchdog outweigh the drawbacks that it gives you.